Hello, this is a continuation of our discussion about series circuits, and today we're also going to talk about parallel circuits. Now, a lot of people think that the parallel circuit was discovered by scientists and researchers looking into the properties of electricity, but that's not really true. There was once a man named Waldo, and Waldo's family wanted to have the brightest house on the block, so they wanted to buy as many Christmas lights as they could to put on their house. And Waldo actually bought a string of Christmas lights that had 2,000 individual lights on the one string. The problem was that when Wally got all the lights up and it stapled them all to his house, so that it was a huge drain on the power supply, and Wally plugged the plug in, and nothing happened. His whole family was disappointed, and Wally scratched his head trying to figure out what had gone wrong. Well, since that string of lights was wired in series, and let's just review our rules for series circuits. So we talked about, we'll say that this is a series circuit, and in this case we just have the 3 light bulbs attached to a 120 volt source right here. Each one of these light bulbs offers 50 ohms of resistance, and we talked about that in a series circuit. There's only one pathway for the current to flow from the negative terminal, trying to become more positive, a more positive circuit, the power of positive thinking. And so if any of these light bulbs fell, then it's going to create an air gap where no electricity can flow, and then you'll have essentially an open circuit, so none of the lights in the whole circuit will light up. And we talked about certain formulas, or certain properties of parallel circuits. Since there's only one pathway for current, the total current is going to be equal to the current through resistance 1, the current through resistance 2, and the current through resistance 3. And it's not additive. In other words, and I believe in this circuit that we did, we measured the current to be 0.8 amps. So that means at any place that I measure it throughout the circuit, whether at resistance 3, resistor light bulb number 2, or light bulb number 1, we're going to get a total of 8 amps flowing through the circuit. And that's because there's only one path for current to flow. We also talked about the formula. Let me get that sheet back up. E is equal to I times R, and then how we could manipulate the formula. So in our series circuit, we knew the value of the source voltage, the electrical pressure, was a potential difference of, or a difference of potential of 120 volts. So and we also knew that each resistor or each light bulb offered 50 ohms of resistance to the flow of current. So what we did was we added each individual resistance, and that's represented in this formula. Let's see if I can get it on the screen here. The RT, the total resistance, is equal to the sum of the individual resistors, R1 plus R2 plus R3. Okay, and so we added those all up. That was 50 ohms plus 50 ohms plus 50 ohms. We got 150, but we didn't know the value of the current. But we knew our source voltage was 120 volts, and our total resistance when we added it up was 150. So then we just used our formula. The I total, the current, total current flow, and measured in amps through the circuit, is the source voltage, or the pressure, of 120 volts divided by 150 ohms, and we got the total current of 8 amps. And here again, this is going to be the same amount of current that's flowing through each of the different parts of this circuit, because there's only one path for the current to flow. Now, back to Waldo and his light problem. Unfortunately for Waldo, with his 2,000 light bulbs, when one of them burned out, since it was in series, that means that the whole series of light bulbs also went out. So Waldo didn't know which one of the bulbs was actually burned out. The only thing that he could do at that point was to individually pull out each light bulb and replace it with a new one to see which was the bad bulb. Unfortunately, excuse me, drink of tea here. Unfortunately for Waldo, as soon as he got and it turned out that it was the 2000th bulb, so he got that bulb fixed and then plugged it in. It worked for a second, but unfortunately, the evil string of lights was playing a trick on him, and so as soon as he got the lights lit up, just for a split second, another bulb burned out, and it was the 1000th bulb. So he had to go back through all of the bulbs and figure out which one was the bad bulb and replace it to get the whole string to light up again. Now, Waldo decided he didn't want to go through this again. He wanted his house to be the brightest house on the block, but he didn't want to have to go through each light bulb to figure out which was the bad one, the one that was with the burned up filament, in order to keep the whole string of lights going. So he decided he was going to take some 18 gauge wire and rewire the whole darn thing in such a way that if one of the light bulbs burned out, it would not affect the voltage or pressure flowing to the other light bulbs in the circuit. And so he essentially wired something that we will represent with our 3 light bulbs again to look like this. And here is a picture of his ingenious invention, and this is the discovery. This led to the discovery of the parallel circuit. Now you'll notice I have the same 3 light bulbs in this circuit, but I have them wired a little bit differently. This time there is not just one path for the current to flow from the negative terminal to the positive terminal. There are several different paths, okay, if we look at the circuit. So what I did is I wired it, or Waldo wired it, since he's the inventor of the parallel circuit, so that right here there's 2 connection points. The current at this little node, or this little junction here, has 2 choices as to where it's going to flow. It can flow down through resistance 1, which is our first light bulb, and then go back to the voltage source to the positive side, or it can flow past R1, go to R2, come down R2, and then back to the positive side. And then notice at R2, same thing. We have 2 possible paths for current flow. Here the current can continue and go down through R2 back to the positive terminal, or it can flow on to R3, go down through R3, and then go back to the positive terminal. This is called a parallel circuit because the various loads or components are wired in such a way that they are in parallel, meaning that there are multiple paths for current to flow. So Waldo rewired his Christmas lights, plugged it in, and now he could figure out which was the bad bulb without having to go through each light bulb individually. Because what happened was, let's say that we have our 3 Christmas light set here, and the first bulb is represented by R1. Let's say that this filament burns out. Well, if this were a series circuit, we'd be in trouble because all of the current would be stopped right there at this open circuit, essentially, where the filaments burned up. But since we have these wired in parallel, now, even though this part of the circuit has become open, there still is another pathway for the current to flow. Now it can still go to R2, and it can flow down and back to the positive terminal, or it can go on to R3 and then flow down and back to the positive terminal. So now the fact that one of the bulbs burns out will not make all of the bulbs quit working. And this is essentially how a parallel circuit works. Okay, let's look at some of the electrical properties of this circuit. Okay, first of all, as you will observe from the picture itself, there are multiple pathways for current to flow. And you will also notice that every individual resistance is hooked up directly to the source voltage. So over here in our drawing, R1 is hooked up directly to the source voltage, R2 is also hooked up directly to the source voltage, and R3 is hooked up to the source voltage. That means that each one of the 3 branches, and each one of the 3 branches there, they all are receiving the full electrical pressure, or the 120 volts. This is different from a series circuit. Let's go to our series circuit again. And we didn't actually talk about this much in the last little episode, but if I wanted to go around and check my math, because we said that the total resistance was 150 ohms, the total current flow was 0.8 amps through each of the points in the circuit. We could go back and check our individual voltage drops at each resistance by using the Ohm's law formula, the E equals I times R. So here we know at this one point there's 50 ohms of resistance to the current flow, but we do know that the total current flow is the same at all points in the circuit, so we know that it's 0.8 amps. Well, if we multiply that out, and we want to find out what the voltage drop is at the first resistance, we would just take the 0.8 amps multiplied by the 50 ohms of resistance, and we wind up with 40 volts. That's not the source voltage, but if we go to each one of the three resistances and we do the same thing, so for E2 we multiply 8 amps times 50 ohms, we wind up with 40 volts. We go to resistor number 3, we multiply the 8 amps by 50 ohms and we wind up with 40 volts. Then we add all this up and voila, we have our source voltage of 120 volts. That's true for a series circuit, but it is not true for a parallel circuit. In a parallel circuit, everything is reversed, whereas in a series circuit, the current was the same at each of the various branches. In a parallel circuit, it is actually the voltage that is the same, and the different currents through each of the branches is what is different. Okay? Now, one thing that can be tricky about this, since there are multiple paths for current flow, that means that there's actually less overall resistance in this circuit than it would be if it were a series circuit. So, and this is really tricky and it's a little bit counterintuitive, but even in the series circuit, since there was only one path for current flow, excuse me, another drink of tea, we had to add each one of the individual resistances to come up with a total of 150 ohms of resistance. But in a parallel circuit, it's different. Since each one of those resistances is also a separate pathway for current flow, there are actually more pathways for current to flow, and the total resistance should be substantially less than the individual, than if I were to add these up to try to add them numerically to the 150 ohms that I would get if I added the resistors up. And in fact, when you add the resistances up in a parallel circuit, you should get a smaller number than the smallest resistance in any one of the branches, of the various branches. So here, when we add our total resistance up, it should be smaller than the 50 ohms that would be for a given branch circuit. Now, there are two ways to do this mathematically, and the first one's called the reciprocal formula, and I have it drawn up right here. So I can find the total by, what I do is I take 1 divided by 1 over 50 plus 1 over 50 plus 1 over 50, and what that is it's the reciprocal of the sum of the individual resistances through each branch. And so if I did all of that, I would come up with the RT of 16.67 ohms. But we can actually take a shortcut here, because all of these resistors, R1, R2, and R3, are all of the same quantity, so they're all 50 ohms. So a shortcut here would be just to take the value of the individual resistor, 50, and since there are 3 of them, divide by 3, and then I get the same number of 16.67 ohms. But the key point here, and it's counterintuitive, is whereas in a series circuit we would add those up, it would be 50 plus 50 plus 50 is 150, because there's one path for current. Since we open up 3 paths for current in this circuit, or actually really more, then it actually lowers the overall resistance, so we can't add the individual resistance values up. We have to do it with the reciprocal of the reciprocal formula to find that resistance. Now, once I find the total resistance, I can plug in the Ohm's law formula just like I would for a series circuit. So what I'm going to do now is, and I know this is probably terrible to see, I'm going to have to figure out a different way to do this, but so I know that my source voltage is 120 volts. We added up the resistance and came up to a total which was smaller than any one of the branch resistances of 16.67 ohms, and I divide that out and I get 7.2 amps. That is my total current that's running through the circuit. Now, whereas in the last circuit we went around to check our math and we did each one of the voltage drops, and then we added the voltage drops, and they should have added up to our source voltage of 120. In this particular circuit we can't do that because the voltage is the same, since each branch of this circuit is connected directly to the negative and positive terminal, and you can see that from my picture here. Okay, so what we're going to have to do is add up find the current for each of the branches and then add that up, and it should equal our total of 7.2 amps. So let's do that real quickly. Okay, so here we have the math. It's pretty simple. I know that I have a 50 ohms of resistance through each branch. So for the current through branch number 1, light bulb number 1, I take the total voltage because the voltage is connected directly to each branch in a parallel circuit, which is 120 volts. I divide that by 50 ohms and I get 2.4 amps flowing through that first light bulb. And since each of these branches has the same resistance value, we can just kind of extrapolate from our first equation and know that we have 2.4 amps flowing through the second branch with the second light bulb and 2.4 amps flowing through the third branch with the third light bulb. When we add all of that up, it should equal our total current for this circuit, which we did the math for, and we found it to be 7.2 amps. And that's how a parallel circuit works. Thanks for listening.